Hi, I'm Sarah.
And I'm Kimberly.
And we're going to be talking about cross-sections. So, a cross-section is the area that you get when you take a function f of x and you accumulate it using a certain shape and it becomes a geometric figure.
We're going to draw an example right here. And we're going to draw the graph of f of x from 0 to a. And this line is f of x. And this little line can represent dx, the change in x. The example says that the cross-section of the f of x is a semicircle. So this is what a semicircle looks like. And this can be represented as f of x. And basically the first step is you find the area. And since it's half a circle, it's 1/2 pi r squared. And so r equals f of x. So you write an integral from 0 to a and plug in the area. And since r equals f of x, you can just say f of x squared. And so this is a visual representation of what it will look like. It's just a bunch of semicircles infinitesimally small under the curve. So you can visualize that.
So it's pretty much the same thing when you do it in dy, but you just have to remember that all of your functions are with respect to y. So if you have a similar line, but this time it's f of y from 0 to a, this is just one dy.
0 to a.
And if you accumulate it using a square,
I'm going to draw what a square looks like and try it again.
then you know that the base and the height will both be f of y.
Therefore the side will too, because it's a square.
So the area of a square is just r squared, but we're just going to substitute in f of y, since in this case that is what r is.
Here are some common areas that you'll need to know for the test. The area of a square, which is obviously just s squared, so therefore f of x squared.
A semicircle, which would normally be 1/2 pi r squared, which becomes 1/2 pi f of x squared.
And then an equilateral triangle, which is just √3/4 f of x squared. These change if they're in dy.
If there's any others, you can just derive them with the information you're given in the problem.